Swayam Prabha. Digital India. Educated India.
Okay, so last class we had started with protein folding mechanism, right. So just a brief recap. So what we did last class essentially was we looked at different mechanisms. We did not go into too much of detail. But we said that there were broadly three classifications. One was referred to as a framework model, where you would form local secondary structural elements and then they would diffuse and collide. So, here you had diffusion and collision of your preformed secondary structural elements. Okay. So, the major topic of our class today would be diffusion. How can we look at a process like diffusion? The second one was nucleation or nucleation condensation, where you form a certain element of the structure and then the rest of the structure. So, that behaves as the nucleus and then the rest of the structure forms just around it. Okay. And the last one was hydrophobic collapse, where in hydrophobic collapse you typically have a certain hydrophobic side chains, they would collapse to form a hydrophobic core and then essentially everything else would follow that event, right. So, after having said this, what we did was we started looking at the first one, which was the diffusion collision, and we said that in the diffusion collision or the framework model, and we said in the framework model, we have to look at the framework model. It is essentially based on the fact that you have certain micro domains, if you remember, certain micro domains. So, these micro domains would be your preformed secondary structural elements, maybe alpha helix, maybe beta sheet, maybe a mixture, right, does not matter. And then once these micro domains are formed, they would, what would they do? They would diffuse and collide, because just diffusion would not give you the final thing, they will have to collide, they have to stick together and then you get the final native structure. Okay. So, typical example of this if you would see would be myoglobin. So, myoglobin typically has this protein myoglobin, it has 8 alpha helices. Okay. So, that means you can consider each helix to be a microdomain, right, and once these helices form, then these microdomains they would diffuse towards each other, they would collide and they would give rise to the final form of myoglobin that you know. Okay. So, again essentially one of the biggest points in framework model is diffusion of microdomains, right. So, how do we how do we understand diffusion? Can we do we have some well defined laws? For example, in thermodynamics, right, you have first law, second law, third law. Now, diffusion is also what? Diffusion is related to kinetics. So, and those kinetics kinetics would also be based on certain well defined laws. So, let us see what are some of those laws. But before we can go into that, we try to understand a term. So, we will start with diffusion, and what we will try to understand is a term known as flux, Okay. So, this is flux is a major component of diffusion, and it is typically referred to as your flow of particles or fluids, right, and is represented by the symbol J, and is represented by the symbol J. Now, if you think about a flux, if you would wonder, think for a brief moment what flux can tell you. See, flux will be dependent upon two things. So, let me write down the expression. So, what happens is this dj, that means a small element of j, is equal to v dot ds. So, what you are looking at is dj, which is equal to a dot product of two vectors. The first vector is v is a vector, okay, and the next one is ds, where s is corresponds to certain surface area essentially, and that is another vector for you, right. And remember, when you have a dot product of two vectors, the final form you get is a scalar form, which is essentially your dj, right. Now, this dj is your change in flux, right. It is not your disk jockey, remember, right. Okay. That was a joke, none of you are smiling. Anyway, that is how joke should be, right. So, how do we define v? So, remember, these are again vector quantities. Okay. So, v essentially can be written as your velocity of flow. So, v essentially is your velocity of flow. Now, it makes sense, right. If you are looking at a flux, you would definitely want to know at what velocity these things are coming out, your particles. So, that is definitely one component. And when these particles are coming out, they have to come out through a certain surface area or certain surface. So, that S represents that area through which it is coming out. Now, if you consider a certain surface, a surface would be made up of very small elements ds, and hence if you would be integrating over the whole surface, what would you get? You would get the total flux, which is j, right. That is what you are trying to look at. So, this velocity of flow is essentially what? Its magnitude. So, v is the velocity of flow, its magnitude gives you the speed, right. And then there is one more thing, is the other thing is its orientation. So, orientation will give you the direction of flow. That means, v is very important from two aspects. One, its magnitude gives you the speed, and the second, its orientation gives you the direction of flow, like through which direction it is coming out, and that is v for you. Then obviously, the other component of this dot product is ds. I mean, let me write this one as equation 1. So, then what is ds? So, what is ds? So, this is how ds is defined. It is the size and orientation. It is the size and orientation of an infinitesimally small area element. Remember, this is the surface area we are talking about. So, this area essentially is a cross sectional area of your plane, because plane is 2D, right, through which the fluid is flowing, through which the fluid is flowing. Okay, that is how you define ds. Now, how do we look at it? Essentially your dj is a dot product. So, what you look at, the way you look at it is like this. So, say you have a plane, this is one way you can look at a plane, right. So, that means plane means you have a surface, you are putting a cross section area, it is like a planar cross section area. So, you can have it like this. So, that means this can be your S and this can be your V, okay, both parallel. Now, then see this plane, so this plane is like this, right. This is your S, this is your V, right. Now, what you do is you move your plane like this, okay. That means you change your direction of orientation or your direction of the velocity flow, that is what you are changing, right. So, it is not necessarily like this, your velocity can also be like this. So, that means you change your plane like this, but remember the way the S is defined, S, which is a surface area element, essentially the part of the surface area, ds is a surface area element, S is always defined as being normal to your planar surface. So, no matter where you change the plane, S is always taken to be normal. Okay. So, essentially what is changing? Then the moment you do this, you start giving rise to what? Angles between your S and V, right. So, then the other way you look at is, say for example, how do I do it? Okay. So, you can now see the way we have oriented the plane was here, now we have shifted the plane like this. So, because the plane is say looking like that, my S is this, and remember S is always normal to your plane, okay. But then see the velocity has orientation now changes, and this is your angle alpha, okay. This is your angle alpha. So, if you would define dj, now if you would define dj, which is what? V dot ds. So, essentially what would it become? It would become V ds cosine of alpha, right, alpha being the angle between these two. And then remember we talked about this angular dependence when we were talking about dipole orientations. So, this boils down to the same thing, right. So, then to get the total flux, we integrate. So, the total flux would then be dj V dot ds, okay, or j is equal to dot ds. So, what is the integration over? Your integration is over the whole available surface. Your surface is made up of ds, right, like ds1, ds2, ds3, ds4 and so on up to ds infinity. And then once you integrate over the total surface, what you get is the total flux, okay. Then how can one define j? I will come back to this, but how can one define j? J can be defined as the amount of flux or the amount of materials you have per unit area per unit time, okay. So, that means j can be defined as the amount of material flowing per unit area per unit time. Now, this amount of material can be anything. The most direct one we in chemistry are concerned with is what? Concentration, right? Concentration is directly related to the amount of materials. It can be number of moles. What is concentration? Is moles per certain unit of volume, right? It can be just it can also be just moles. Just it is the amount of material. It does not matter what units you take it in. Whatever you do, you will always get the same thing, which is the flux, which is J. Okay. So, this is how J is defined. Now, this was related to something known as a force field or a flow field. So, what we will now do is we will move away from this exact notation and we will try to simplify things and get a better idea of what flux is, okay, from a very practical example. So, that means the next point we discuss about is how to get an idea of flux, which is J. Okay. So, again we do the same thing. What we do is we take a cross sectional plane, okay, and what we say is that the distance or the length of this edge is delta x, and we say that the plane has a cross sectional area A. The plane has a cross sectional area A. Okay. Now, we also say then that concentration of particles flowing is C. Concentration of particles flowing is C. Now, if your length element is delta x, if your cross sectional area is A, then what is your volume element? What is your volume? A delta x, right? Okay. Now, if this is your volume, you are given the concentration which has say some moles per unit volume, then what is the total number of particles flowing through this volume? So, total number of particles flowing through the volume is given by, see, we are talking about number of particles, right, which is C times the volume, which is A, then delta x. Right, clear? Okay. See, how did we define J? J was defined as the amount of material which is passing through per unit area per unit time, right. If that is what a definition is, and if that is what we have to stick to, then for J, what is the numerator? It's total number of particles we just derived, which is C times A times delta x, right. Now, what do we have in the denominator? Per unit area, right. So, we should be having what? A, then per unit time. So, if you have delta x, I should be writing delta t. So, this is the definition of J, right. Now, see how it simplifies, then what is J now? So, J is equal to C times delta x over delta t, and delta x over delta t is what? V is dx over dt, right. So, then I can write J is equal to what? C times V, right. So, this is equation 2. So, then you have a very direct idea of flux. So, what is flux proportional to? Your concentration, and also along with that what? The velocity of flow, right. So, that is your flux. Now, this equation, you keep this in mind, we will come back to this pretty often as we discuss. Okay, so, now that was the idea of flux. Now, let us talk about some well defined diffusion laws. If we ever have to talk about diffusion, what are the different laws we have to keep in mind, or different laws we can use? Say for example, someone asks you what is the thermodynamics first law, that is conservation of energy, right, and then you come up with these thermodynamic equations, state function, path function, all these things, right. Now, similarly here, so for example, if you are going to solve any thermodynamic problem, you would first start from that principle or start from that law. Similarly, if someone asks you, give me the diffusion profile or tell me what is going to happen after this amount of time, we need to have an equation, because we just cannot understand without looking at a certain law. So, these laws are referred to as the diffusion laws. So, the first, or the person who actually came up with a set of laws, do you know his name? His name is Fick's diffusion laws, right. So, let us look at diffusion laws. So, Fick's said that your flux J is equal to minus d delta C over delta x. This is equation 3, and this is referred to as Fick's first law. This is referred to as Fick's first law. See, the idea is very simple. The idea is, if I have the flux is directly proportional to what? What is del C over del x or dC over dx? It is essentially a concentration gradient, right. It is a concentration, how your concentration is changing over the length interval dx. And what is d? D is a certain proportionality constant, right, which is intrinsic to the system you have under investigation or you are talking about. Okay. So, what you can write here is d is a constant which is referred to as diffusion coefficient, okay, and del C by del x obviously is your concentration gradient. Now, what does the negative sign mean? The negative sign implies where is your flow from? Your flow from is always a region where you have high concentration to a region where you have low concentration. That means, flow from high concentration to low concentration. Okay. Now, so if you are talking about the flow of a particle, what do you think is the force behind this flow? There has to be a force behind this flow. What is the force? The force essentially is a concentration gradient. If there were no differences in concentration, or if there was no difference in concentration between whatever that delta x, that 2 points you are talking about, the flux, then there would not be any flow, right. So, that is typically what happens at equilibrium. That means, at equilibrium everything has matched out, equilibrium has been reached, that means there would no longer be any net flux change. That is what happens at equilibrium, but until unless you reach equilibrium, you have to satisfy what? The equilibrium condition. That means, how can you reach equilibrium? What happens at equilibrium? Your chemical potential becomes equal, is not it? Your chemical potential becomes equal. So, understand this, the force behind this diffusion is what? Equalization of chemical potential, right. Now, in the same line, so this is just diffusion law based on the concentration gradient. There can be two other things. In heat, if you have heat flow, see, heat flow also occurs, that is also diffusion, right, convection and all these things, right. Then in heat flow, what is the driving force? I will not write it down. What is the driving force? In particle flow, it is concentration gradient. In heat flow, what is it? Temperature gradient, right. Okay. Then there is one more. You remember Ohm's law, right. So, in Ohm's law, if you have a flow of current, what is the gradient you are looking at? Potential gradient. Potential gradient. So, think about this. All these three fundamental things, be it particle flow, be it current flow, be it heat flow, would be defined by very similar set of equations, where the flux is essentially proportional to what? The gradient, whatever gradient it is, times a certain constant, which is a proportionality constant specific to that thing you are considering, right. So, this is a picture you should be having when you think about some sort of diffusion occurring, does not matter what it is, whether it is current flowing, diffusion essentially flow, right, whether it is particle flow or whether it is heat flow, right. So, I will see whether I can talk about some of these in the later classes or in connection with this, but for the time being what we are going to center ourselves on is particle flow, right. So, then if we go deeper into it, what we say is that the force for particle flow comes from the tendency of equalization of chemical potential. On the equalization of chemical potential, and we are talking about particle flow or concentration flow. Now, since we have already introduced now chemical potential, what we know is the chemical potential is a mu x, right, can be written as mu 0 plus k T ln C of x. See, I have taken k, I have not taken r. So, it is just what is the difference? It is difference by an Avogadro number, right, that is what it is. There you would talk more, this is per molecule essentially. Now, how would you relate force to chemical potential? So, think about this. When you talk about force, what is force? Force into distance is work, right. Now, remember, force is also equal to minus dV over dr. Do you remember? Force is defined as minus dV over dr. What is it? It is the potential energy gradient. Now, think about the dimensions. Force into dr is equal to V. V has energy units. So, essentially force is what? Force is derivative of energy, okay, right. Now, then think about this. If it is dV over dr, can we write force is equal to minus dμ over dx? So, that it was r is distance, here it is x, we are talking about one dimension. Now, if think about mu, which is chemical potential, it is essentially what? It is molar Gibbs free energy, right. Now, you are talking about energy again. So, this also has energy units. So, then what I can write is I can define force as, I can define force to be minus over d of x. In analogy with what we had, where f is equal to minus dV over d of r, I am not writing that. Okay. Now, if we have this, say this is equation number 4, then I take this mu of x and what is my force going to become then? So, my f is going to become d of dx with a negative sign, then I have mu 0 plus k T natural log C of x. Okay. What happens to the first term? What happens to the first term? Right. So, mu naught, it is a constant. So, the first term essentially is 0. So, what are you left with? So, what you are left with is minus d of dx k T C x. So, this I can write as k T I take out, right, and then I can write d natural log of C over dx, and see whether I can simplify this further as minus k T over C d C over d of x. So, what is d ln C? D ln C is essentially what? d C over C, right. So, that is how we have expressed it. Okay. Now, Where have you seen this dc by dx before? Remember, you have seen this dc by dx where? When we were talking about j ray, right, minus d times dc over dx. So then what you can understand is, it does not matter for any flux, whatever fluxes we talked about, I can write a general expression for j to be equal to L times f, let this be 6, I should have written this earlier. So, this is a general expression for j, which is for flux j, right, where L is your proportionality constant and F is the force causing the flow. So, F is the force causing the flow, right. Again, what are the different forces we just discussed about? One was, we saw this concentration gradient, that means equalization of chemical potential. The other one was your temperature gradient for heat flow, and the other one was your potential gradient for current flow. So, then this particular general expression of flux covers all those things, right. Now, let us start being specific. So, you look at the one we just derived, force, then I can say for particle flow then I use J is equal to L times F, and I have already defined F before. So, this is equal to minus L k T over C dc dx. This is equation number 7 for me. Okay. So, here you see, here you have an expression where J is equal to dc over dx times a certain constant or certain value, right. Compare this equation equation 7 with Fick's first law. What was Fick's first law? J was equal to minus d dc over d of x. Okay, I forgot what the equation number was. What was it? 3. And if you compare, then what is the value of d? So, then d is equal to L k T by C. Okay. Now, this can be further written as d is equal to U k T, where U is equal to L by C, and this U is defined as mobility, and this U is defined as mobility. Okay, that is how you define it. U is defined as mobility. Then you can see, if U is defined as mobility, then what is inverse of U? It is inverse of mobility. So, what is inverse of mobility? It is essentially a friction, isn't it? It is just inverse of mobility. So, then 1 by, so the inverse of mu would correspond to friction or friction coefficient. Okay. So, this is for you to have a general feel of what diffusion is all about. Okay. Remember, this is only Fick's first law, right. We have, if there is Fick's first law, we have to have a second law at least, right, because that is why it is called first law. Now, having said this, what are the types of diffusions we can have? One diffusion is referred to as steady state diffusion. Now, what do you mean by steady state diffusion? What I mean by steady state diffusion is concentration gradient is independent of time. Okay. So, if your concentration gradient is independent of time, and remember J is directly related to concentration gradient with via that proportionality constant d, which is the diffusion coefficient, then I can write schematically, if this is J right and this is J left, that means if this is the flux on the left hand side of this element and there is a flux on the right hand side, then if it is concentration independent, gradient is time independent I mean, then what should I write? I should write J left is equal to J right, and if I do that, then I can write minus d del C over del x left is equal to minus d del C over del x right, because that is how you define J, right. D is constant. So, from here what are you going to get? From here what you are going to get is dC over dx on the left, dC over dx to your right. Then again what does it mean? The concentration gradient on the left hand side is equal to the concentration gradient on the right hand side, right. No matter how much time is elapsed, you still have the same concentration gradient. Okay. Right. So, this is referred to as steady state diffusion, and Fick's first law, as you can see that is what we have used, is essentially an example of steady state diffusion. Okay. So, Fick's first law is an example of steady state diffusion. Now, one more thing is, now suppose I have a concentration gradient which goes like this. Say this is C and this is x. Okay. So, say the concentration gradient is something like this. Okay. Now, when I talk about a concentration gradient, what am I talking about? I am talking about dC over d of x. Then essentially what am I talking about? I am talking about the slope of the respective what? How do you find the slope of a curve? You draw a tangent at that definite point, right. And remember your flux J is proportional to the concentration gradient. Okay. So, think about a point here, and say think about a point here. Here you have J1 and here you have J2. So, where is the flux more? Remember D is the same. So, where is the flux more? In 1, right, because what? The slope is more, dC, the gradient is much more than in case of 2, right. So, we can write J1 is greater than J2. So, if you would ever try to picture out what a flux is or what it should be depending on, this is what depends upon your slope of the curve, which is essentially your concentration gradient dC over d of x. Okay. So, that means if you are given if you are looking at a diffusion profile or diffusion flow, and if you want to know where the flux is greater, you simply draw a tangent, take the slope, essentially take the slope of that point and you understand where the flux is more, essentially where the slope is more. Now, if you are going to have something known as steady state diffusion, then you are going to have something which is non steady state. Like if you have an equilibrium situation, you are going to have a situation which is non equilibrium, right. So, then let us look at non steady state diffusion. So, here the concentration profile is dependent on time. That is I can write C can be written as C x t. So, it not only depends upon the distance x you have travelled, I am talking about one dimension now, but it also depends upon the time that has elapsed, okay, from the moment you have started looking at it. So, then what it means is, again if you try to draw a schematic, if you try to draw a schematic, say this is C, this is x, then I can have say different situations. Okay. So, this is T3, this is T2, this is T1, say T3 greater than T2 greater than T1. It just tells you that your concentration profile is no longer the same at whatever time you are considering. At T3 you have a different gradient, you can see slope is different, right. At T2 you have a different gradient, because the slope of the curve obviously gives you the gradient, and at T1 again you have a different gradient. So, this is a typical example, or this is a typical schematic of non-steady state diffusion, and non-steady state diffusion is the one which you are actually interested in, because remember, if you are having a diffusion, what will happen? Particles will flow, and if particles flow, then particles will flow from one place to the other. So, there will be a depletion in one case, that means particles would be missed from there, and there would be a population in one place. So, that means what is happening? You are having a depletion, you are having a population, that means the concentration gradient is no longer same, it is varying with respect to time, how much time you give it. Okay. So, that is why this non-steady state diffusion is much more interesting than a normal steady state diffusion, right, and that is something we are looking into right now. So, then if that is the case, how do we try to model non-steady state diffusion? What we say is, now before for steady state diffusion we were only interested in del C over del x or dC over dx, but now it is not only that, we know C is a function of x, but C is also a function of t now. So, what we say is dC over d of t is equal to minus dJ d of x, and okay, what would this equation number be, if you can help me with this? So, 8, right. Good. So, dC over dt is equal to minus dJ over d of x. Okay, this is where you start from with a non-steady state diffusion condition. Now, you already know what J is, right. So, therefore, I can write dC over d of t is equal to minus d of dx. What was J? Minus d dC over dx, right. This is how we had defined J before, because flux definition does not change, right. Flux definition is not changing. What you are saying is, remember, when we talked about steady state, what did we say? That if you are taking J left and J right, both of those are equal, that is what we said. But now we are not saying that. What are we saying? We are saying that because it is non-steady state, then J left is not equal to J right anymore. Then there is dJ over dx which is coming in, because that depends upon the length you have traversed. Okay. So, you simplify this, then I have dC over d of t. So, negative sign now goes away, right. So, I should be having what? d C over dx squared or dC over d of t. I remove the del square. So, this one I can write del actually, because I should not be mixing partial with full derivatives. So, anyway, so dC over d of t is equal to d2c over dx squared. This is equation number 9, and please remember this is Fick's second law of diffusion. This is Fick's second law of diffusion. Clear? What is the assumption here? There is one small assumption we have taken when we derive this. Especially look at this stage and then we come here. What is the assumption? The assumption is d, right? D is independent of x, right? So, what is the assumption here? That d is just a constant, it has no dependence on x. That is why it is not differentiated. Okay. Good. So, this is your Fick's second law. Now, again what does this Fick's second law say? What is a second derivative? A second derivative is essentially what? Your curvature. Second derivative is essentially a curvature of whatever curve we are looking at. Okay. So, what this law relates you to is, it does not relate you to the concentration gradient, right. What is your concentration gradient? Your concentration gradient is dC over dx, but what does it relate to? It relates you to the rate of change of concentration gradient, because rate of change is what? D dx of dC over d of x. So, then Fick's second law, what it does is, the second law relates to the rate of change of concentration gradient. Okay. Unlike your first law, where it was only related to what? The concentration gradient, not the rate of change, because there the concentration gradient on the left or on the right were same, right. Okay. So, again if we try to understand it schematically, as I said, that the second derivative is related to your curve's curvature. The second derivative is related to your curve's curvature, okay. And keeping that in mind, let us look at three different situations, okay, because it is related to your curve's curvature. So, let us look at this one. Then I will look at another one, and then we look at another one. This is C x x x C C. Okay. Good. Now, there are three different curves having three different curvatures, not exactly three different curvatures, there are three different profiles, I would say. Now, the first one, remember we are talking about dC over d of t is equal to d c over dx square. Okay. Now, the first one, what is the curvature? Is it positive or negative? It is a positive curvature. The first one is a positive curvature, right. If the first one is a positive curvature, if this is a positive curvature, then look back at this equation. This is positive, right. Then obviously diffusion constant cannot be positive, cannot be negative. Then that means dC by dt, it also has to be positive. So, what does it mean? Then C and T should be going in the same direction, that means having the same sign. So, that means if C is increasing, or if T is increasing, C is increasing, and so on, right. So, then C go like this, T also goes like this, or the other way around. That means if T is decreasing, C is decreasing too. The sign convention has to be the same, only then you will get positive, that is it. Now, what are the next one? The next one would be having a negative curvature. So, here if you write it like this, here the curvature is like this. So, obviously say C increases, T decreases, or C decreases, T increases, T decreases, and so on. Okay. Now, what are the last one? You have both. You realize that, right? See, this, here it is positive, and in this case it is negative. Okay. So, this is an example again where you have, this is just a schematic. This is an example where you have both the profiles coming in. Okay. So, again if you would think about the change in concentration with time, which is dC over dt, what would you relate it to? You would relate it to the curvature of the curve we are looking at. That is the take home point. Okay. So, before we wrap up the class, I will just tell you one more thing. So, if you look at Fick's first law or second law, we had only talked about one dimension, which is x or y or z. Here we have resorted to x. So, then in 3 dimensions, the first law will become J is equal to, see what was the first law, minus d times del C over del x, right. So, here it would become minus d, then what should I write here? Del C, is not it? This is in 3 dimensions, right, and this would be what, equation number 10, I guess. Okay. And then the second law would be dC of d of t is equal to what? D, right, del squared C. Where what is, do you know what this del operator is called? Del squared is repulsion. What is del? Yeah, it is essentially is something known as gradient, Look this up, look up gradient of vectors and all these things, you will be having a much better feeling. Gradient, divergence, curl, because all these are vectorial notations, right. If you can relate it to this, those things you will be having a much better feeling of this. Okay. So, anyway, so del square is essentially what, if you have ever wondered, del square is essentially del dot del, is not it? That is how you get del squared. What is del equal to? Del is del of del x with unit vector I plus del of del y with unit vector j plus del of del z with unit vector k, and if you are going del dot del, which is a dot product, then only I dot I, j dot j, k dot k, they stay, the other ones go out. So, that is why you have del square over del x square plus del square del y square, del square del z square, and that is how it comes, right. So, okay. So, at least we have some idea of what the diffusion laws are, what they try to tell us. So, next class what we will do is, see, when we are talking about diffusion, your particle is diffusing in the solvent, in the medium, but then when the particle is diffusing in the medium, it also, apart from this force of diffusion, which is a concentration gradient, it also experiences another thing. What is that? It experiences an opposing force. What is that? Dielectric constant is not a force, which gives rise to what? Friction. That means in your solvent, if you would be able, if you would really want to picture it, you would have to bring in what? The frictional force too, and that friction force gives rise to, you can integrate it this, that means whatever j you have, or whatever del c by del t you have. What is del c by del t? It is essentially equal to minus del j over del of x, right. Now, j would be having 2 components, one component is because of this concentration gradient, and the other component would be because of the frictional force, right. So, these two you combine and you will get something which is known as the Smoluchowski equation. I do not know whether you have heard of that, but that is what we will look at in the next class. Okay.